Good afternoon, everyone. I hope you can hear me.
Good afternoon.
Hello, can anyone hear me?
Yes, we can get you.
Okay, so we're going to wait a little, but we'll start soon. I think there are only six participants. So try informing your friends, those who are not yet in, so that we should start. Okay, so I think we're going to start. We start or we wait for some people. Hello?
We can wait a bit so that when they come, they shouldn't start making you say that no, bad network, what. So just wait a bit so that they have no excuse.
Okay, so wait. Continue telling your friends, I think. No, continue telling your friends. Okay, I think we'll start. Those who find us will try to catch up with, yeah, time is moving. So, did you guys understand the previous exercises that we did? Hello, I need your participation. Did you guys understand how to get the SHA and the Z from the previous exercise that we did, or we do a rappel on one of them?
We can go through.
We can try to go through like one. Yeah.
Okay, so we'll do a petit rappel of one. The one we had charges outside. So it was a sphere with the radius A. Let me get. So it was a sphere with radius A. Okay. So it was a sphere with radius A, and then it had charges outside. And then they were telling us to use the theorem de Gauss to calculate E, the electric charge, and V, the potential à l'intérieur et à l'extérieur de la sphere. So we took, for instance, A, this point here was the point we're finding in the interior, and this point was the point we're finding in the exterior. And then we say the distance from the origin to the point in the interior and to the point in the exterior, and the point in the interior, we give it the name ara. So we said ara, this is ara à l'interior, this is ara à l'exterior. This is the point at which we're trying to find the champ and the potential à l'exterior, and this is the point where we're trying to find the champ and the potential à la interior. So what we did is that we used theorem de Gauss, which is flux is equals to E ds, which is equals to Q interior over epsilon 0. So we said for us to have flux, we can integrate this. So we integrated it, so meaning we also integrate this guy here. So when we integrate this, we'll have flux is equals to E, this integral of this, which is equals to this guy here. So we said we'll start with the à l'exterior. So à l'exterior means we're trying to find the electric charge here and the potential here. So what I explained is that we're going to come up with a Gaussian surface. I think I remember mentioning something about the Gaussian surface. So the Gaussian surface is like we establish another surface. So establish a Gaussian surface, And then we're going to, so after we do this, we're calculating the champ and the potential à la exterior. So after we establish the Gaussian surface, we're going to have our R. Our R is less than A. No, à la exterior, sorry. À la exterior, our R is supposed to be greater than A. I hope you guys can see what I'm doing. Our R is supposed to be greater than A, à la exterior. The R is greater than the radius because we're finding it from outside. So our R is greater than, sorry, our R here is greater than A. So at the exterior de la sphere, our R is greater than A. Our R is greater than A. So we're going to have EDS is equals to Q, the charge over the epsilon 0. And then what we say that if we integrate ds, we're going to have S. So a la exterior, we're going to have ES is equals to Q int over epsilon 0. We're still using the Gauss law. And then we know that for a sphere, so we have this. So we have a sphere like this, and then if we draw the Gaussian surface. So the Gaussian surface will be around. So we'll have something round like this. And then we know if we have a sphere, if I draw a, let me just draw it. If I draw a sphere where the point P lies, so I'm going to have, oh my God, okay, sorry. Okay, so if I draw a sphere around this point, I'm going to have a sphere around this point like that. And then what's my radius is going to be my R. Do you guys get what I'm saying? So from the origin to the point P, that's going to be my radius because I've for that Gaussian surface that I'm going to establish. So if I'm going to have a sphere around this, this sphere, which is including the point that my R is going to be my radius. So after that, I can establish that. After that, I can establish that my S for a sphere, the surface area of a sphere is equals to 4 pi R squared. We did this in math. So my S of a sphere is going to be 4 pi R squared. So if you don't know, surface area of a sphere, volume of a sphere is 4 pi R cubed. So the surface area is just the integration of that, the differentiation of that, sorry. So we're going to have this S is equals to 4 pi R squared. And then where there is S in our equation, we put it. So here we're going to have E times our S, 4 pi R squared. The R is for radius in the formula. So since we've established that we've got a Gaussian surface around and from the point origin to the surface, what P is, that's the radius. So we're going to have 4 pi R squared is equals to Q over epsilon 0. And we're trying to find the champ. Don't forget, we're trying to find the champ. So we make E the subscript formula, and this is what we're going to have in the direction ER. Are there any questions? So this is the champ for the exterior. And then when we're taught to calculate the champ à l'interieur, so à l'interieur we have something like this. Let me try to draw that again. So we have a sphere. We have a sphere and the charges are outside. So it's trying to tell us that there are no charges inside unless they tell you that there are charges inside. So in this case, they have indicated that the charges are outside, the positive charges, it's positively charged on the surface. So we have that and we have that around. So here it's positively charged around. So I'm trying to calculate the E à l'interieur. So our R is less than A. So maybe I'm trying to calculate a point here. A point here in the interior of the sphere. And then this is my origin. This is my origin. Then we've established that that's my radius, which is A. There. So maybe I'm trying to find the champ at the point E. It can be in any part of the interior of the sphere. So my R is less than A. I use my theorem de Gauss, E ds is equals to this over this. So since inside here I have no charge whatsoever, there's no charge in this sphere. So my charge here is going to be 0, which is going to result in everything being 0 because my charge here is going to be 0. And if there's no point in me even actually continuing to find my ds, because everything I'm going to multiply here, I'm going to find 0. So my q int is equals to 0, my shine is equals to 0, so my electric field is equals to 0. Are we clear on that part?
Yeah, we're clear. There's a question.
What?
I'm saying we're clear. Now I just want a clarity. Does it mean that when we don't have a charge, like inside the, we always are going to have 0, or only when there are charges in it? That's when I'm going to have ED.
No, usually if they give you a drawing and they specify where the charge is, either outside or inside. So if they tell you to find the charge inside and then the charges that have indicated them outside, the charge there is 0 because there's no charge in it. Or if they give you the charges inside and then they tell you to find the charge there, you're going to use the charge that you have there, whether it's positively charged or negatively charged, but they will indicate for you where the charge is in the sphere, whether it's inside or outside.
All right, thanks.
Yeah. And then now we're going to try and find the potential. So we're going to find the potential a la interior and a la exterior, the same thing that we're doing. So we're going to find it a la interior, a la exterior. So we discussed that potential tells us how much energy a single point charge at a given location will have. So that's simply what we're trying to calculate here. And then in our last call, we came about the equation that gives us a relation between the champ and the gradient. So now we're going to start with L exterior. So L exterior, don't forget our expression for L exterior. Our expression for L exterior is this guy here. So our champ L exterior is equals to Q over 4 pi r squared epsilon 0. So we're trying to find the potential L exterior at the point P that is outside the sphere. So L exterior we have E is equals to negative grad of V. And then our champ in L exterior we've said that it's equals to this. So now we're dealing with a sphere. We're dealing with a sphere. So we're going to go back to our coordinate Cartesian, coordinate what's that? Coordinate Cartesian, coordinate spheric, and coordinate cylindric. So we're dealing with a sphere. So definitely we'll use coordinate spheric. So we say that the gradient, the expression for gradient in the coordinate spheric is equals to this. Are we together on that part? I need your participation, guys. Are we together?
Wait.
Yes, so we said our gradient is equals to this, right? So our champ is only in the direction ER. If we had an option, we would indicate, this is simply trying to tell us that here, if we had plus, let me say, plus, okay, I think there's something wrong with my sensor. Okay, so we have this E in the direction ER. So meaning E is in the direction ER. On our gradient expression, we have in the direction ER, we have in the direction E phi, and we have in the direction E theta. So what this implies is that we have our relation for E is equals to negative grad of V, which I've rewritten here. So meaning, let me try to explain this. So if I have my E is equals to that, my E is equals to a negative grad of V. So meaning all this is going to be negative. This, I'm going to multiply this by negative. Do you guys get what I'm saying? All this expression, what's wrong with my sensor? Okay, so all this expression is going to be negated. This whole expression here is going to be negated if I'm to equate this expression to E. Do you guys get what I'm saying? So if I say shine is equals to negative grad of V, so meaning this whole expression will have to be negated here. Sorry for that, and here. So if I have that, I already know what my E is. My E is on in one direction. So I'm going to use one direction. In this direction, it's 0. In this direction, it's 0. So I'm just going to have this direction. So I'm going to say E, which is this, my SHA is equals to this, the gradient, which has been negated here. Are we together there? Are we together there?
Wait, are we negating because according to the formula, E is equal
Yes,
to negative gradient?
it's negative grad of V.
Okay.
Yes, so we have negative there. So our whole expression will be negated, but in the Champ expression, we don't have Champ in the direction E phi, and we don't have Champ in the direction E theta. So we're just going to deal with direction ER. So we're going to have this is equals to our negative of our grad V, which is this. So this, the ER and the ER can cancel. That's some simple math. So the ER and the ER can cancel both sides. And then what we're going to remain with is Q is equals to this, which is Q over 4 pi r squared epsilon 0 is equals to negative dV over dr. Are we together there? And then when we equate this will give us equals to dV over dr is equals to negative. So we've just changed the location of the negative. And then we're trying to find potential. We know potential is the V that we're looking for. So we're going here, we're going to make dV the subdivision formula. So when we make dV the subdivision formula, our dV is going to be equals to negative Q 4 pi r squared epsilon 0 times dr, which is what we have here. And then for me to have my V, I'm going to integrate my dV. So I'm integrating both sides. So I integrate dV, I integrate both sides. And then what I'm going to have as my V is going to be this expression here. Because this is dr, so I'm expressing it in dr. So my r here, my r will have to be separated. So I'm going to have the constant, which is negative Q over 4 pi epsilon 0 integral of 1 r squared dr. And then what's the integral for 1 over r squared? The integral for 1 over r squared. Can anyone help us with that?
Wait, Chamanzi,
Yeah, sure.
I'm lost in the 1 over r squared. Like, how did you get to that?
So we said our Champ is equals to Q over 4 pi r squared epsilon 0, right?
Yeah.
Yes. So we changed the subject formula. We had dV over dr, the negative, we made it go the other direction. So we have dV over dr is equals to negative Q 4 pi r squared epsilon 0, right? So we are trying to get the value of V, but we have dV. So we make dV the subject of formula. So meaning the dr is going to multiply this side. So we're going to have dV is equals to negative Q 4 pi r squared epsilon 0 dr. Are we together? So
Yeah.
now integrating with the derivative dr. So what we now expression we have r. So what we're going to do is that we're going to remove the r squared in our expression. We move it the other side. It's like we separate. So now we're remaining with the constants. We have negative Q 4 pi epsilon 0 as the constants. In integral 1 over r. We've just separated the r squared. It's not been separated, but yes, it's been separated from the constant. So we have negative Q 4 pi epsilon 0 as the constants. You cannot integrate constants. So we move them the other side of the integral. So this is what we have. And then the r squared, because we're integrating with respect to dr. So this is what we're going to have. So we're going to have 1 over r squared dr. Are we together?
Yeah.
Yeah.
Are you sure?
Yeah, I'm sure. I was lost on why the r squared because I didn't notice that it came from the 4 by r squared.
Yeah, came from the formula. So the integral of 1 over r squared integration, it's a simple integration. So the r squared, 1 over r squared is the same as r over negatives r2. So let me just draw it. So my 1 over okay. So 1 over r squared okay. 1 over r squared is equals to r negative 2. Do we agree on that?
Wait,
So if we integrate r to the power negative 2, what are we going to have? Can someone help me with that?
Should be 1 over r.
we're going to have to add 1.
Huh?
We're going to have to add 1 to the power. Then the value we get, we'll have to divide by the whole expression.
Yes. So what our result here is going to be equals to negative 1 is going to be equals to negative r to the power negative 1. Right?
Wait.
So if we take this negative, the r down, we're going to have negative 1 over r. Am I correct?
Wait.
Yes. So if we have a negative q for 4 pi epsilon 0 times negative 1 over r, that the negatives are going to cancel. I'm going to have this. And then when you integrate, it's your integration plus a constant. So in this form, I integrated, I had negative 1 over, or negative r to the negative r to the power negative 1 plus a constant. Those are the rules of integration. So plus a constant, any constant c. So what I'm going to have here as a result is v is equals to q 4 pi epsilon 0 1 over r plus the constant b, which is equals to q over 4 pi epsilon 0 r plus b. Are we clear? Or I repeat?
Say clear.
Yeah.
It's
clear?
clear. Yeah.
Okay.
Just a minute.
Sure.
Screw up a bit.
Scroll, just a minute. Okay, let's scroll up a bit. Here.
Yeah, just there after the exterior.
After the exterior.
Yeah.
Okay.
Yeah. Again. Okay. Okay.
Go down.
I go down again.
Okay. Question, or you want to copy something?
Yeah. Just repeat how the none can. The q over 4 pi r squared is equal to that. Just explain there again.
Okay. So is anyone who's understood who would want to explain?
What was the question again?
Why the q 4 pi r squared epsilon 0 is equals to negative of this?
I think that's the equation which you earlier gave us. The one on top, just above gradient v is equal to.
Yes, this
So
is.
we were replacing the e with that. We are replacing e with theta over, is it q over 4 pi r squared epsilon 0? Er in the direction of er. Then we equated it here. Then you said since it was equal to negative grad v, we had to write negative dv over dr er. Now you said all these one earlier on you gave us grad v is equal to this Chilong equation we have seen e. Now we don't have r, we don't have this 1 over my r sine thing, we don't have them, so it will be simply cancelled. We'll just remain with the dv over r er in the direction of er. Now taking plus that negative which came with grad v, we add it there, then we continue going down there.
Yeah, so basically what he's from saying is here we know that E is equal to negative grad of V. So here I'll write E is equals to, sorry, my sensor is bad. So I have E is equals to my expression grad V, but our expression here is saying E is equals to negative grad of V. So I'll multiply this whole expression by negative. So I'll add a negative here, which is multiplying this whole expression. But since my sha is only in the direction ER, this is 0, this is 0. So I'll have our E, which is Q over 4 pi R squared epsilon 0 in the direction ER is equals to negative dV over dr in the direction ER. So clear? That's how we came up with the, this expression.
All right.
Okay. I think Kenneth raised their hand.
It was a mistake.
Okay. So this is the potential à l'extérieur. Because we've used the expression the champ à l'extérieur. So if we're finding E à l'interior, we found that we're finding V à l'interior, we found that our E was equals to 0. I hope you guys remember. So our E was equals to 0 à l'interior because there was no charge. So if we're finding the potential à l'interior, we still use the same thing. So we have E, which is equals to 0, is equals to the integration of, so E is equals to negative grad of V. So now we're trying to find V. So what are we going to do? E is equals to 0. So remember when, okay, if I have an expression, sorry, if I have an expression 1 over X, and then I'm told to find the gradient for that expression, what I'm going to do is that I'm going to derive this expression. So here simply, this is simply what I'm doing. So E is equals to negative grad of V. My E is equals to 0. So I'm going to have 0 is equals to negative grad of V. So for me to have V, I'm going to integrate this whole expression, negative grad expression. So I'm going to have V is equals to 0. Then if I integrate this side of my equation, it's going to give me a constant. Integration of anything is the integration plus a constant. So I'm going to have integration of 0 is 0 plus a constant. So I'm going to have V is equals to a constant. And then that constant, I gave it a letter A. So my potential à l'interior is going to be equals to a constant, which we give a letter A. Are we clear?
Oui, c'est clair.
Wait, so we move to today's, what we're doing today. So today, we're going to do something similar. This is our question. So we have soit un fil indéfini uniformément chargé de density linéaire. So we've been given the density linéaire. This guy here. On se propose de calculer le potentiel au point P à la distance R du fil. So a fil is a wire, or yes, a fil is a wire. So peut-on trouver V à partir de l'intégrale curviligne? So they've given us our potential. Here, they've given us our potential, and then they're telling us to find the exact value of V. So we're supposed to find our value, exact value of V from this expression that they've given us here, from our V expression that they've given us here. And they're saying explique. So do you get the question? So they've given us a field that is uniform uniformément chargé de densité linéaire. And then they've given us an expression, and then they want us to calculate the exact value of V from this expression. And then they're saying explique. So that is what we're going to do. So in short, we're still trying to find our potential. So we're going to do that. Sorry. So, okay, so we're going to do a petit rappel. So we have, sorry. Okay, so we have Q. This is a point charge, Q. This is in the direction U. This is a point M, where maybe we're trying to calculate the champ at the point M. The electric field produced by this charge at the point M. So remember that Q is the point charge, M is the point where we're trying to calculate the electric charge from, and then we have this direction U. So we have OM, the direction of OM. Sorry, I didn't indicate my OM. So this place where the Q is, let's say it's O. The point O to M is has the distance R. So we know that OU is a vector expressed in this form. The direction OM over the actual distance from O to M, which is this. So we have R, which is the same as R vector over R, because the distance from O to M is R, and U is represented in this form. So I'm going to have this. And then we remember our actual expression for potential. Potential is equals to Q over 4 pi epsilon 0 R plus a constant. So usually our constant is equals to 0. So we're going to have V is equals to Q over 4 pi epsilon 0 R. And then what else do you need to remember? So we have our expression for densité volumique, densité linéaire, and densité surfacique. So when we just change the subject of formula, we have dq is equals to this, dq is also equals to this, and dq is also equals to this. So in this expression, we've been given, oh yeah, so if I have dv potential, so I'm still dealing with this guy. So I have v is equals to q over 4 pi epsilon 0 r. So I have dv. So if I have dv, where there is q, I'm going to have dq. So I have dv is equals to dq over 4 pi epsilon 0 r. And then dv is equals to, yeah, dq over 4 pi epsilon 0 r, epsilon not r. So I'm going to have v is equals to, if I, if I integrate it. If I integrate v, I'm trying to get the expression for v. I'm going to have v is equals to 1 over 4 pi epsilon 0. The same thing that we did. This is a constant, so we bring our r at this side. So we have dq over r. So we're going to have v is equals to this 1 over 4 pi epsilon 0 integral of dq over r. So here what is tried, this is dv is equals to dq over 4 pi epsilon 0. So we're trying to get an expression for v. Yes, we're trying to get an expression for v. So v can either be written as this or as this, expressed as an integral. So you can have v is equals to 1 over 4 pi epsilon 0 integral of dq over r, having this as a constant. So this dq can be written as this in densité linéaire if we're trying to find it from volume chargé or linéaire or surfacique. So we have dq is equals to rho dv when you're taught for your volume chargé or this. So where there's dq, you can either have this or this or this according to what the question told you. So in our question, we've been given the densité linéaire. So literally we've been given this guy here because we're trying to find the volume along a field, which is a wire. So we've been given linear. So this guy is going to come here on our dq. So we're going to have v is equals to 1 over 4 pi epsilon 0 integral this dl over r. Am I clear, or there are questions up to there?
There's a question.
Sure.
How did we lose the constant there on top? V is equal to Q over 4 pi epsilon 0 R.
Here on top,
Yes.
I said usually a field, they give you, unless they specify the length of the field, but usually when they just tell you, no, a field which is uniformément chargé, it means it's moving from infinity, negative infinity to positive infinity. You don't know, they haven't specified. So usually when you are given that our constant, we assume that our constant is equals to 0. That's why in this case, we've assumed that our constant is equals to 0. So we have V is equals to Q over 4 pi epsilon R plus a constant, but we've been given a field that is, they haven't told us, that they haven't specified the length. So our constant is going to be equals to 0. So we're going to have V is equals to Q over 4 pi epsilon 0 R. And then we're going to play around with this. So if we have dV is equals to dq over this, and then we do our integration.
Thanks. Then can you remind me this symbol which I'm seeing here, what it means and where we used it?
The row.
No, the one which you have used here.
Yeah,
in
it's
V.
for linear X. So along a line, we're trying to calculate charge density along a line. Sorry. We're trying to calculate charge density along a line. Along a line, we use densité linéaire chargée. So along a surface area, a certain surface, we use this guy here, surface X, and a certain volume. If they give you to find the charge density on a certain volume, a certain volume, yes, a volume, you use this guy here, rho dV dq. So that's why we have, so we have rho is equals to dV. Sorry, we have rho is equals to dV over dq. What am I saying? So rho is equals to dq dV. Yeah. So yeah. So now this expression is trying to, this expression is rho is equals to dq over dV. So if you've been told to calculate the charge density over a certain volume, area of volume, so this is what we have. And then this is the same thing if you've been given a certain surface area, like a certain surface area, we use this guy. And then if you've been given to calculate the charge density along a line, we use this guy, this expression, this symbol right here. This symbol is equals to dq over dl. Which is what I have here. So we've been taught to calculate it along a line, along a line. So that's why we've used the linear dl, this symbol dl. If we're taught to calculate maybe along a surface, we would have used this guy or this guy if they gave us a certain volume. So they said it's linear, so we use this guy. So our expression V is going to be 1 over 4 epsilon 0. The integral, this over R. Yeah, so from our question, let me go back to our question. Sorry. From our question, yeah, our question is here. So this is figure 1 for number, yeah, for question number 1. So let me go back to our question. So yeah, so I've been given a field in the uniformément chargé de densité linéaire. On s'est proposé de calculer le potentiel au point P, voir figure 1 à la distance R de field. So we're going to see our figure 1. This is our figure 1. So this is what we've been given. So this is our field, and then we're told to calculate the potential at the distance P on the line. So the P point can be here. So the P can be here, can be a point charge here. Oh my God, can be a point charge here, a point charge here. It can be anywhere along this line. So they've just given you this drawing to help you when you start your calculations. So we go back to our answers. Okay, so I have so I have, that's the same thing. So I have my field. Okay, so let me draw it again for you guys to understand better. So I have a field. I have a wire. I've been given a wire. I've been given a wire of length that I don't know. So I've been given a wire. It goes up to infinity. So you can just indicate that by writing dots. Yeah. So we haven't been specified the length of the wire. So I've been given a wire, and then I'm being told to calculate the potential at a point P, r distance from the wire. So I'm told to calculate the potential at this point here. So this is my P. So I've got P, sorry for that. So I've got P with the XY in the XY plane. So I'll explain why we're saying it's in the XY plane, because yeah. So I've got a point P. I've been told to calculate a point, the potential at the point P, at the point here, which is r distance from the wire. So I've been, so I will do this. This is my r. So this is the point I'm trying to calculate my potential as. Sorry, let me just make it a bit bigger. Okay, this is my point P here, right here. Yeah, so this is what I have here. So this is my wire, and then this is the r distance from here to this P here. So this is my point P, which I've indicated P, X, Y. And then, yeah, so this is what I have here. So now we're told to calculate the potential. So for us to calculate the potential, we have to know some things. Yeah. So what we're going to have here, so we're going to have this. So if I divide, I have a wire. So if I get a segment of this wire, I get a segment of this wire. I get a segment of this wire. Maybe this length of the wire. I get a small segment of this wire, and then the height of this segment, I'm going to give it dy, the name dy. Yeah, so the height of this segment, so it's like a wire, then I've just gotten a small portion of that wire, small length of that wire, and then I've given the height of the wire dy. So if this length is uniformly charged, as we've been taught, so meaning if the charge in this wire is Q, if our charge flowing through this wire is Q, and we get a segment of that wire, the charge on that segment of the wire is going to be dQ. Are you guys following?
Yes.
So our segment, if they've told us that our field is uniformly charged. So if it's uniformly charged, so meaning there's a certain charge that is in this field. So if I get a portion of that wire, my charge is going to be dQ. And the length of the part that I've gotten of the wire, I've given it dy. So meaning from here to the segment of this wire, so from here to here, it's going to be y. From here to here is going to be y. So I'm going to have my y here. from the center here where we have drawn our line to the segment where the segment starts is going to be y. The height of this segment is going to be dy. So if I extend this line, okay, so if I extend this line, okay, let me go back to my drawing. So if I extend, I've extended the line. This is my point P, I've extended the line. This is my y or z. So I explain that later. So this can be my y or my z. So we're dealing with a wire. So in this case, that's why I chose to use DL. It can be for a line, DL. So I use DL, or you can use DZ as well. So in this case, we chose to use DZ. Or here we can, if we can have Y or Z or L. So in this case, I'm using Z. So my portion from here to here is Z. My height here is DZ. My charge is Q. So this line I've indicated here that it's from positive infinity. We don't know the length, so positive infinity, negative infinity. This is the distance from the line to the point charge where we're trying to calculate our potential. This is the point charge P. We have extended the line. This is the segment of the wire that we're going to use. So if I draw an electric field vector, we said that for a point charge, the electric field acts outwards. So if I draw the electric field vector between the segment and the point charge, my electric field vector is going to come in this direction. Okay, so it's going to come in this direction. So if I extend it, I'm going to have my DE, my electric field vector. And then the same thing, I choose a segment, just a part of that line, of that wire. The same thing applies DQ, and this height of this segment is DZ, and from here to here it's Z. And then I extend I draw a line. I draw the electric field vector between the point and the segment. It's going to be in this direction, which I have right now. And then E, sorry. So this electric shunt has got electric field working in the X direction, in this direction, and in the Y direction. It's a point. I said the electric field acts outward. So we can have it coming in the Y direction, in the X direction, and in this direction. The same with this, from this segment to the point charge. So I can have it in the Y direction, downwards. Oh my God. Okay, so I can have it in the Y direction, downwards, and in the X direction. So what I can see from this is that this is coming like this. So this shunt is going in the opposite direction from this shunt right here. So this, in the Y direction, my shunt is equals to 0 because they're going in the opposite direction. And then in the X direction, they're parallel, they're going in the same direction, so they will add up. So for easier understanding, we know that our DE here is gotten from our DE can also be expressed in the X direction and in the Y direction. If we use from this segment to the point, our E is going to be extended, and we can also have it in the X direction and in the Y direction. From this part of the segment of the wire, we have E extended, we can have it in the X direction, or in the Y direction or the Z direction, and in the X direction. So we've got the shunt going this direction and shunt going this direction. They can cancel because they're going in opposite directions. We've got two going in the same direction, that parallel. We add them. So paraison the symmetry. So the net electric field in the Y direction due to the symmetry of the rod is 0. So in this Y direction, it's 0 because they're in opposite direction. In this direction, they're adding. So if I'm having DE, my DE here, which is this guy here, my DE is equals to DY DE in the direction Y and DE in the direction X. So this is what I have. So DE is equals to DEX plus DEZ. So my DEZ is equals to 0 because they're in opposite directions. So what I'm going to have is that my DE is going to be in the direction DEX. So I'm trying to calculate SHA because the SHA, we have an expression that has SHA and grad V. So we need to know our SHA for us to be able to get our potential, sort of. So are there any questions on this diagram right here? Are there any questions? And gladly answer them.
Can you kindly repeat why we got 0 as our DEZ?
So our shamp in the direction EZ. Okay, so I say that we've chosen two parts, two segments, and on the wire. So we're trying to calculate the shamp. This is this vector. This line here is trying to connect the segment and the point. So the direction of the shamp is going to be outwards. So we extend the line. This is our DE. The same thing. Okay, so if this is our DE, so our DE is going to be in this direction. And then this is a point chart. The point chart, the electric field is always outward. So we can have SHA from this SHA here. We can have it also in the Y direction or the Z direction. And we can also have it in the X direction. And then the same thing if I go to this part segment of the wire. So I try to make, I draw the electric field vector between the segment and the point charge. So my SHA is going to be, if I extend the line, my SHA is going to be also, I'm going to have SHA in this direction. So bear in mind that I'm also going to have, I can also have SHA in the Y direction or the Z direction and in the X direction as well. So this SHA is going opposite direction. This one and this one are going in opposite directions. So the addition of this is going to be equals to 0. And this SHA, they're both going in the X direction and they're parallel to each other. So we're going to have them, we're going to have to add them. So my DE is equals to DEX plus DEZ, in that for me to have DE, my DE, this DE expression, I have to move from DEX. I have using trig. This is now we've introduced trig. So I'm going to have a triangle here. So I'm going to have to move in the X direction and in the Y direction. So DE is just like A squared is equals to B squared plus C squared. So I have DE is equals to SHA in the X direction and SHA in the Y direction, So if I have SHA in the X direction and SHA in the Y direction, we've already agreed that in the Z direction or the Y direction, it's equals to 0. So I'm going to have my SHA is equals to DEX as a result, because my DEZ is going to be equals to 0 because they're in negative or opposite direction. Are we clear?
Yeah, it's clear.
Yeah, so we move from this. These are just notes. So
Wait, before we move on.
So that's, is that a question?
Yeah.
Huh?
Like, how did we come up with that angle up there? I know it's fascinating, but I'm a bit lost. Yeah.
Oh, so, okay. I haven't even explained about the angle yet, but yeah. So right now we're just from talking about why we have all these lines. So this line and this line I've explained, right? This DEZ and opposite. So this. So okay, I'll explain to it when I'll explain about the angle when we get there. So this is the field and this is our point. This is the distance from the field to the point charge and R. So that the distance from the segment of the wire to the point charge, we'll give it the name R. And from the middle of this wire to the segment, we'll give it Z. So Z or Y if you want, but yeah, in this case, we've given it Z. So we have Z, we have R, grand R, and we have petite R. Yeah, so that's what, so we're saying NBR is dependent on Z. So they're saying R is dependent on Z. So if I choose a segment, this is a Y, it's infinity, it's going to infinity. So if I choose a section of if my segment, I chose it to be here, my R was going to be different. My R is going to be different. So my R is dependent upon my Z. This is what this NB is trying to say here. But my R is not, my R vary par. So for the distance from the wire to the point charge is going to be the same, whether I change the distance from the segment to the point charge. So if I choose a segment here, if I chose the segment here, for instance, my R is going to be different. So my R is going to be like this, but my grand R is going to be the same. The distance from the wire to the point charge is going to be the same. So this is what this NB is about. And then, yeah, so don't forget to try and calculate the potential from the expression that we're given. So V is equals to this. So you know where the infinity is coming from. The infinity is coming from the length of the wire. So we haven't been given the length of the wire. The length of the wire is running from positive infinity to negative infinity. And this is our expression. This is our dq over r. Yeah, so this, which we can simplify, V can be equals to, so this is a constant, this is a Greek constant. So we can bring it out. We have 4 pi epsilon 0 from positive infinity, negative infinity, 1 over r dz. So we've just dismantled this guy is a constant. So we've taken to the constant side. And then we have dz over r, which is what we have here. So from our drawing, our R, let me go back to our drawing. So we have this expression now, so we have to find the value of R. So we go to our expression, to our drawing. So our R, you can see where our R is, what we named as our R. So our R is equals to Z squared plus R squared. Our R squared is equal to Z squared plus R squared. This is using trig. So this is our hypotenuse, this is our opposite, this is our adjacent. Now that's when we add in the triangle, the angle issue, because it's helping us with our trigonometry to get our expression for R squared, for Z, and for grand R. So introduce our theta here. You can introduce any angle. It can be alpha, you can call it alpha, or you can call it theta. Yes, in this case, we use theta. So introduce angle theta here for our trigonometry. So now we have a hypotenuse, we have an adjacent, and we have opposite. So our R is equals to Z squared. Our R squared is equals to Z squared plus R squared. Am I correct on that one? Using our trig. So we have our R is equals to R squared is equals to Z squared plus R squared. And if I want to make, I want R, and I want an expression for R and R squared. So I just square root both sides. So I square root. So I square root both sides. Because I want an expression for R alone. Sorry about that. So this, the square root and the 2 cancel. So I have R is equals to Z squared plus R squared. Then where there is my R, I put my expression for R that I've found. Are there any questions up to there?
No.
Okay. Okay. We continue then. So I'm going to have my R is equals to this. Where there's R, I've replaced with my expression for R that I've found. So now I need you guys to pay attention. So we're still trying to calculate the expression for V. We're trying to find the exact value for V. So now we're going to try to find a primitive. So we're integrating this. So before we integrate this, we've got limits positive infinity to negative infinity. So we can change this by using in ADMA as you go on, in Analyze, sorry. In Analyze, as you go on, you learn about parity. If a function is odd or if a function is even. So you learn about even functions and impair functions. So let me just hope you understand how that is. So on this slide, this is what I wrote. I just wrote a little bit just that when you're revising, you can remember. So parity in analysis, it's like parity is like pairing. So you can have an odd function or you can have an even function. So if we have a function f of x avec une range a to negative a, so here we can have 1 to -1 or positive infinity to negative infinity, which we have in our case. F of x is pair if f of x is equals to f negative of x. And f of x is impair if f of x is equals to negative f negative of x. So that explained simply is equals to, if I have a function, f of x with the limit a to negative a, if it's pair, this expression can also be written as 2 integral of a to 0 f of x. So in this case, in our case where I have positive infinity to negative infinity f of x, it can also be written as 2 integral of infinity to 0. So if it's impair, I'm going to have integral of a to negative a, f of x is going to be, so if the function is impair, you're going to have your function is equals to 0, or it can also be written as 0, or it's equals to 0. So in this case, if my function is impair, I'm going to have integral of infinity to negative infinity is equals to 0. So in this case, my function is pair. Yeah, in this case, my function is pair. So function, I wonder you guys are thinking about which function am I talking about? I'm talking about the integral here, what we have here, this guy here. This guy here. So this guy in my case, this guy is pair, excuse me. So this guy is pair. So in our function f of z is equals to this. So if we'll just say that this function, we give it the name f of z. And then what we're going to have is, we're now going to integrate this guy here with respect to dz. So what we're going to have is, so now we're going to talk about primitive. So primitive is an antiderivative, which is the same as integrating. So an integral of, if they tell you to resolve on primitive, the x to the power 4, meaning your x to the power 4 is your dx dy, or dy dx, whichever you want to put it. So if they tell you to resolve on primitive, the x to the power 4, your x to the power 4 is your dx dy. And then if they tell you to find the primitive, it's like you're just integrating what you have. So if you integrate x to the power 4, you have x to the power 5 over 5 plus c. This, they tell you to find the primitive of this. It's the same as you just integrating it. So the same of them telling you find the integral of this. So we have this is equals to this. These are just examples I was trying to give you. So 1 over x dx, when you integrate it, you have ln x plus c. And then e to the power exponential x dx, when you integrate it, you have the same thing. So you cannot, if you integrate e to the exponential x, you have the same thing plus a constant. That's for integration. And then this is the same thing. So we have some functions in analysis that are given. So if I have 1 over z squared plus r squared dz, the primitive or the derivative of this guy is going to be ln z plus z squared plus r squared. Yeah, so what we're going to have here. So we are given a list of functions, or when you type, or when you, during your research time, you just go type primitive of functions. They'll give you a lot of them, not these obvious ones like 1 over x or x to the power 4. They give you stuff like this, 1 over z squared plus r squared dz. The primitive of this is going to be ln z plus z squared plus r squared. So you'll find a lot of primitives there. And then, yeah, so the primitive of this function is going to be equals to this. So from my explanation, I said sorry. I have this, so I'm going to have 2. Yeah, I'm going to have a 2 there because my range has changed. So negative infinity to positive infinity, negative infinity can be written as 2 of whatever the function that you have from positive infinity to 0. So I'm going to have this now after I integrate the function. And then now after that, I'm going to have v is equals to 4 pi this constant, I mean, over 4 pi epsilon 0. So if integration, you know how to integrate. So if I put my infinity in my expression, so I'm integrating with respect to dz. So if I put my infinity where the z is, everything is going to be infinity. So if I have ln a and where there's a, I have to put infinity, I'll have infinity. So here I have infinity. If I put my infinity here and I put my infinity here, my whole expression is going to be equals to infinity. And then minus integration, you have to subtract. So I have, I have infinity here, infinity here. I'm going to have infinity. Not forgetting the 2 in front. So that I have a 2 here, sorry. I have a 2 here. I have a 2 in front here. So I'm going to have infinity if I put infinity here. And if I put 0 where there's z, here where there's z, minus, with the minus, don't forget the minus. So if I put 0 here, and I put 0 here, I'm going to have ln r, which is what I have here. So anything, infinity minus anything is infinity. So we're going to have pi over 4 epsilon 0 is equals to times infinity. I mean, because this minus this is going to give us infinity. Sorry. So this is going to give us infinity. It's like infinity minus 1. It's going to give you infinity. So we have this times infinity is equals to infinity. So our v is approaching infinity, and that's our answer for the exact value of potential from our expression. So are there any questions, any queries, anything? Please ask. Yeah, ask questions, ask if there's some part you're not clear of, I can explain.
Can you just go up a little bit where there's value and pair?
Where there was what?
Pair and impair.
Okay, so you guys don't have to, sure, just a minute, I'm going to go up. So you learn this, you learn in analysis, you learn about this. So this right now is looking complicated because you haven't done the parities. Yeah, but you you learn.
What is on the left side here? Is it
Well,
V is equal to lambda on the left side here?
here
No, continue going to the left.
it's infinity minus ln r.
No, to the left,
This
far left. Oh,
far left.
far right. I don't know if it, yeah. Continue going up.
This
What is under 5? Under 5
under
is 5 1.
this is
Now,
expression for one.
just below that.
Oh no, this is, don't mind. This was I just rubbed it.
Oh,
Yeah, it's rubbed. So true. Yeah.
In terms,
Huh?
that expression for v, is it integrated or what?
Which expression?
That one down below 5, like v, the first one.
This one?
The first one, v is equals to lambda over 4 pi.
Or yes, because we said we agreed that this, there are a lot of expressions. So if you're taught to find the integral of this guy is equals to this guy. So the integral of this guy is going to be equals to ln z plus z squared plus r squared. So we've integrated this guy and it's given us this. So where there was our expression for that, we put our function that we found with our limits positive infinity to 0, not forgetting our 2. From our parity, we said that if we change the limits and this function is pair, which we have in this case, our function is pair, we're going to have two times whatever function we have from with the limits positive infinity to 0 or 1 to 0, if in the case we had 1 and negative 1, or 1 to 0. So in this case we have this, and then you know what this means. So meaning you subtract, so you have to subtract this with infinity minus this expression with 0. So we're integrating here, we integrated it with respect to dz. So meaning our z is our variant, our z is our field. Remember we said our z is our field. So if we get a segment, anywhere along, so our z is the one that's moving. So it's not moving, our z is the one that's varying. So as our length for z varies upon the length of the segment. So if this is our wire, I get, this is my point P, our P is here, my P is here. So I can get a segment here, I can get a segment here. So meaning this is my Z, this is my Z, or my Y, whichever you would want to call it. So whichever, yeah. So this is my Z, my distance from the segment to the point is Z. So my Z is the one that varies. So I can get this, a segment here, I can get a segment here, I can get a segment here. So the line is up to infinity. So our Z is the one that's varying. So which is why we're integrating with respect to Z here. So I have this constant over 4 pi epsilon 0 ln this. So where there is our Z, we replace with our value. So we have infinity and we have 0 there. Sorry, we have infinity and we have, oh my God, okay. Sorry, just a minute. Yes, so we have infinity and we have 0. So we know integration, if you've been told to integrate, you have to also to not miss this step where you subtract the limits. So we are subtracting our limits. So if we put infinity in our function, we are going to have anything times, or yes, anything times infinity is infinity. So when we put infinity here, we put infinity here, we're going to have infinity. It's going to be ln infinity, which is just the same as infinity. Infinity minus, if we put 0 here, we put 0 here, we're going to have ln r, which is infinity minus ln r. So anything subtracted or added to infinity is equals to infinity. So we're going to multiply this constant over 4 pi epsilon 0 times infinity, which will give us infinity. So our v is approaching infinity, and that's our value of v, our potential.
Okay.
Yeah. So I will go to our next question. Our next question is, sorry, go to our first question. So they actually even gave us the 1 over 4 pi epsilon 0. They gave us our dq because they told us it's density linear. So we just had to, follow some steps. And then our second question is, trouver le champ électrique à partir de son expression pour une distribution linéaire individuelle et potentielle électrique V. So they're telling us to calculate the champ from this expression that we have here. Yeah, so they're telling us to find the champ électrique from this expression that we have here. So which is what we're going to do. So now we're trying to calculate the champ. So these things are easy. You just play around with the formulas, and as you go on, you get to know some like the functions, you know which one is pair, which one is impair. You do that in these. You prove whether a function is pair or impair, so you know most of them. And then the same with the parity. You know how to well, you know which function is pair, which one is odd, which one is even. You'll be shown how to prove it, and then it will be a bit easier for you. So yeah. But for now, this is what we have. So we've been told to calculate the champ E. Yeah, we've been told to calculate the champ E. So we still have our expression. So we have E is equal to negative grad of V. So we've been told to calculate the champ from that expression that we have, that we've been given. So we know that if we have an expression for champ, if we remember, I don't know if we remember. So our expression for champ is equals to E is equals to E. Oh my goodness. Okay, so our expression for champ, okay, I think I'll just say it. Our expression for champ is equals to dq is equals to q over 4 pi epsilon 0 r squared. If you go back to the note, you find it in the direction u. That's our expression for champ. So in this, this is what we have here. So we have dq, we have de. So if we have E, we have our E is equals to Q over 4 pi epsilon R squared. Now in this case, we have dE, so we have dE is equals to dQ over 4 pi epsilon 0 R squared in the direction U. Our sham is going to be going outwards as well in the same direction as, so it got the direction U. So we have linear, that they've told us in the question that the distribution is linear. So we have dE is equals to, where there's our dq, we replace with our expression, which is the constant dz in the direction u. And then now I need you guys to follow me. So our u, okay, so we'll go back to our drawing. Yeah, we'll go back to our drawing. So our u is in this direction. So we said our direction from O, M is in this direction. Just a moment. Okay. Just a moment, sorry. Okay, so we continue. Sorry about that. So we have our SHA expression for champ in the direction u. Then I'm going to draw something. So y our u is equal to our sine theta e minus sine k. So we are going to have this. Okay, let me just not confuse you. Let me go back to the drawing. So if I go back to the drawing, it's here, sorry. I have my DE here, so this is my DE, so I can have this. Let me draw. So I consider my SHA DE, so I can have this. Oh my God. So if I project, okay, why is my sense? So I have this, and then this is my line, and then this is my DE. So if I have a point charge along the line, along the wire, it can be represented as this. So I have this, oh my God. So I have this P, a point charge here, and then meaning the direction of the champ is outwards. So it can be going in this direction, which we have indicated here by this. So we have this DE, which is the DE that we are showing here. So our DE is here. So if we have our DE here and we have our DEX in this direction, our DEX in this direction. So this is the X direction. We established this is the X direction. This is the Y direction. So we have our DE in this direction. We can have our DE in this direction. So meaning for us to have our DE, which is in this direction, for us to have a base vector in that direction, how have we moved? So we move like this, or we can move like this. So for us to have the base vector here, so we say this base vector is U. So we have our U. Our U is equals to, using, going back to what I explained, I think that was in the first school. So we have our theta here. We have our theta here. Our theta here. Which is the same as this using angles. So I'm going to have my opposite, my adjacent is cos. So I have cos in the Y direction. So I'm going to have cos. I have cos in the Y direction. Yeah, so I have, so I have cos E. I have cos, my sensor is very bad. Okay, so I'm going to have sine in the opposite. Sine, I mean in this opposite. So I'm going to have sine in this direction, which is parallel to this guy here. So this guy can be dz or whichever you call it. So using our three-dimensional plane, this is our k, and this is our, we take this as our k and we take this as our x. So I am going to have sorry, my sensor is very bad. So I'm going to have U is equals to our sine, which is in the opposite, which is parallel to this guy, and it's in the negative direction. And I'm going to have my x, my opposite, which is my adjacent, which is cos, and then it's in the x direction. So this is what I have here. So I have my U is equals to my sine, my opposite, which is in the k direction, and I'm going to have my cos, which is in the I direction, which is in the x direction, I mean. So this is what I have here. So I go back to my expression. I go back to my expression. Where is it? Okay, I think I missed it. Okay, yeah, so I have this drawing right here. Sorry. So I have this drawing right here. So I established that this is not my theta, sorry. So my angle, I try to draw my angle. Let me try to draw my angle. So if I have a line like this, and then my field was coming in that direction, I'm going to establish my theta at this point. So if I have my theta at that point, I have in the opposite, I have sine, which is moving in the k direction. And in my adjacent, I have cos, which is moving in the e direction, which is what I have here. Sorry. Yeah, which is what I have here. My u is equals to cos e minus sine k, because my sine is in the negative direction, this guy here. So this guy is parallel to this line. So this guy is parallel to this line, and sine is my opposite. So I have negative sine k plus this guy here, which is cos E. So I have my U, my established U is equals to cos plus minus sine k, which is what I have here. And then if I replace where there is U, I put cos E minus sine k, I'm going to have this expression. So it's going to multiply with each of the functions. So I'm going to have my expression times cos minus plus my expression times negative sine k, which I'm going to have here. Yeah, so which I'm going to have here. So let me just wrap this. Okay. So this is when I have multiplied everything. So I'm going to have that. And then remember when I said there's no sha in the y direction. That's why our y was equals to 0. So it's the same thing. So in our k direction, our k, which is our z direction or our y direction, our shamp was equals to 0. So our shamp was equals to just in the x direction. So I'm going to have horizontal symmetry E is equals to the shamp in the x direction only, because in our y direction, we said that our shamp was going in opposite direction and it gave us 0. So I'm going to have, so I'm going to have sha is equals to this guy only in the x direction, because in the y direction it's equals to 0. So I'm going to have my total sha is going to be dE is equals to this in the x direction. And then if I integrate this, this is my dE. So if I'm trying to have my dE, we're trying to find our sha, we integrate our dE both sides from negative infinity to positive infinity to negative infinity. So what I'm going to have here is that I'm going to integrate. This is my constant. So my constant before the integration symbol. So I'm going to have my integration of from positive infinity to negative infinity of the field dz r squared cos in the direction x, cos theta in the direction of x. So that's what I'm going to have there. So yeah, so just like we did in the last one, we found an expression for r squared. Yes, we had to find an expression for r squared. And in this expression, we find the expression for r squared. So we're going to express the r and the z in function of theta. So now we have a theta. That time we had r is equals to grand r plus zr. There was no theta involved. So this time we have a theta. So we're finding the z and the r in the function of theta for us to be able to integrate this expression. So we're going to first the r, the z in function the d theta. So our z, okay, so let me try to go back to our drawing. So this is the drawing. Oh, have I passed it? Okay, I've passed it. So this is the drawing that we have here. So I'm trying to find the r and the z in the function of theta. So I'm going to have my theta. For me to have the r and the z in the function of theta, I have my, so I have the z over the r. Okay. Yeah, so I'm trying to express, just a minute, something theta, tan theta is equal to z over r over adjacent. Okay, yeah, so I have, this is what I have. So I'm trying to find an expression express the z and the r. Sorry, it's this r. So if I have this is tan. So I can use tan. So I'm going to have tan theta. So I'm trying to express the z and the r in the function of theta because I have an angle cos there, and I'm trying to integrate my angle cos, my function that I have there. So I'm expressing dz and dr in the function of theta. So for me to have dz and dr, I have my adjacent and my I have my opposite and my adjacent. So you know that the function that just deals with opposite and adjacent, you're going to have a tan. So tan is equals to, your tan is equals to, let me try to write it. So my tan is going to be equals to my tan theta is going to be equals to, my tan theta is going to be equals to SOHCAHTOA. SOHCAHTOA is opposite over my adjacent. So I'm going to have tan theta is going to be equals to Z over R, which is what I have on that equation. So I'm going to have this. Yeah, which is what I have here. So I'm going to have tan theta is equals to Z over R. And if I make Z the subject of formula, I'm going to have Z R tan theta. Z is equals to R tan theta. So we're trying to express dz and dr in the function of theta because we have dz and r. So we're going to have this is my z expression is equal to z is equals to r tan theta. So my dz, I have to differentiate my z. So my differentiation of z, which is r tan theta, I'm going to have dz is equals to, so the differentiation of tan theta is 1 over cos squared theta d theta. So my differentiation of tan is 1 over cos squared theta d theta. So now I have an r, which is a constant. So a constant, so I'm going to have dz is equals to r over cos squared theta d theta. And then where there is my cos, so don't forget in my expression, I still have a cos theta. So my cos theta is equals to r when you go to our drawing. So our cos theta, yes, so our cos theta, we can get our cos theta from, our cos theta is our adjacent over our hypotenuse. So our adjacent over our hypotenuse is cos theta, cos theta, or cos theta is equals to, cos theta is equals to our adjacent, which is our grand R, over our hypotenuse, which is our petite r. So we're still trying to express the r and the z in function of theta. So we found our expression of, we found our dz in function of theta. Now it's our small r that is remaining to be expressed in function of theta. So if we express our dr in function of theta, we have cos theta is equals to grand R over small r. And then we make small r the subject of the formula. We're going to have what we have here. We're going to have this, what we have here. So our r is going to be equals to r over cos theta. And then our r squared, because we have r squared here, our r squared is going to be equals to r squared over cos squared theta. So we just squared what we have here. And then from here, we're going to replace now. So we're going to replace in our actual equation what we found. So we've expressed dz and dr and the expression in function of theta. So our dz, we found that our dz was equals to r cos squared theta d theta. So we put it here, and our r squared is equals to this, replace here. So what we're going to have is this guy here. So our dz was r over cos squared theta d theta times or over our r squared. So if you make r, you put r over, so it's all this over r squared, And then you know that your cos square theta will come on top and your r squared down, then times your cos theta, which you have here. This cos theta is from here. This cos theta that we have here. So yeah, so that's what I'm going to have. Then all this, when I try to simplify it, I'm going to have, when I try to simplify this, I'm going to have my final expression is going to be pi over, constant over 4 pi epsilon 0, integral of from positive infinity to negative infinity of cos theta d theta over r, which is what I have there. And then if I, so this is what I'm going to have, cos theta d theta over r. So now I'm going to still try to integrate this because I was just trying to simplify. So I have the constant 4 pi epsilon 0 r, integral of from positive infinity to negative infinity cos theta d theta. My 4 pi, my pi over 2 to negative pi over 2 is coming in the fact that this is my line. So we already discussed that this is our field, and this r is the distance from the field to the point charge. So if my r, my z varies, so I can choose a point here. I can choose a point here. The segment, my segment can be here. So if I choose a segment here, my r is going to vary. So my r is going to be, my r is going to be in this direction to the point. So my theta is going to increase. And then if I choose a point here on the field, I choose a point here, for instance, my r is going to change. So my r is going to be moving from there to there. And then I have an infinite wire. So if I continue going on top, choosing my segment, I'm going to remain with a point where my r is equals to 90 degrees. 90 degrees. I don't know if you guys can imagine that. So if I go on my r here, so my r is going to increase. I choose another point here, my r is going to increase. There's going to be a point at infinity when my r is just going to be in this vertical position. Going to be in this vertical position here. Yeah, so this angle here is going to be equals to theta. So this is where this theta is coming from. So if I'm going to, because we have an angle, so I'm going to, so I'm going to have 90 to negative 90, because the same here, I've got segments on two sides of the line. So the segment here, the same happens if I a segment here. So the r is going to be increasing, it's going to be increasing until I reach a point of infinity where the angle is 90 degrees. So I'm going to have my limit from positive 90 degrees to negative 90 degrees. And then if I integrate my cos, I'm going to have sine, If I integrate my cos, I'm going to have sine, and don't forget to put the limits. So if we have this, we integrated our cos, we have sine, and our limits are still there. And we replace where we put positive 90 minus negative 90, we're going to have 2. So this subtraction here is going to give us 2, and our expression for shine is going to be equals to this over 2 pi epsilon times r, grand r. So I think most of you are lost. So you can ask me questions and I'll gladly answer.
Yes. Can you scroll up a bit where you introduced the tan theta?
Why introduced theta?
Tan theta r equal to z.
Why introduce theta r? Here.
Yes, somewhere, yeah. Z is equal to tan theta. Then You had to
theta.
replace Z
had-
with tan theta, right?
Yes, I had to replace.
Then why
well, here- Mhm.
why did you first differentiate it, then integrate it first, then you had to put the integral of tan theta into that equation while there was still that integral sign?
No, I have dz. I do not have z. So here, what happened here? We had to change, since I have cos theta, so we have to look for an expression for dr. We have to express dr and dz in function of theta. So I have dz here. So going to my diagram, if I'm trying to express z in expression in terms of theta, I'm going to have tan theta is equals to z over r. And then in my expression, I have dz. I do not have z. So if I had z in my expression, I would have just put this expression. But I have dz. So what does dz mean? Dz meaning it's the differentiation of z. So dz is the differentiation of z. So what do? I differentiate my z for me to have dz. So for me to have dz, I differentiated my expression. My r, I'm going to consider my r as a constant. So the differentiation of tan theta is 1 over cos squared theta, d theta, which is what I have here. So my expression for dz now is what I'm going to put here. And then now I'm going to express my r squared or my r in function of theta. I'm just playing around with trig identities, but we're going to do another expression where you can find the same thing but using Gauss theorem, which is a bit simpler and it doesn't involve a lot of steps and calculations. So yes, this is using the long method. So if we want to find SHA, this is what we have. So dz here, we put our dz, which we found by integrating z. And then our r as well, we go back, our r, we know we can get our r from having cos theta is equals to grand r over petite r. So we have r squared. So we just square what we have, and then we replace everything where it's supposed to be. And then when we replace, we're going to have things that are going to cancel each other out. So this is the step where we have here. Did I answer your question? Oh.
Yes. Can you again scroll down a bit? Just a bit.
Down again?
Just here. Then to replace the derivative of z, which was in form of tan, right? Which gave you r over cos squared theta.
Yes.
Then you had to multiply them. That's where we could see them canceling themselves. See?
Yeah.
Then remaining with cos theta there. Then down there we had, don't scroll.
Just here?
Take me back wait, just up a bit, again, yeah, just here. The denominator for cos squared theta was r squared, right?
Yes.
Then on the other side, you had r over cos squared theta. Now, canceling themselves here, where are we? Oh, okay, it's clear.
It's clear?
Yeah,
So,
I was wondering why we had over r here. You had to cancel r there with this r squared, then you had to remain with r.
yes. So this is, someone raised their hand.
Yes,
And-
I have a question. How did you come up with those limits, 5 over 2 and negative 5 over 2?
So this is my field, right? So we say that this is our field, and then we introduced our angle here, theta. So I was saying we are differentiating with this, our z or our y, whichever you decide to call it, is our one that is varying. So we picked a segment. In this case, we picked a segment that was here. We got a segment that was here. that was here. So in another case, we can get a segment that was here. We can get a segment that is here. So meaning our R keeps on varying. Our R keeps on varying, and our theta keeps on increasing. So we can get an R here, our R from here. So our R will be different. Sorry about that. So our theta will increase. So this is an infinity line. We don't know where it's ending. So if we get our segment is equals to this, it's here. Our R is going to be, so as you can see, our R keeps on increasing. So there's going to be a point along this line when our R is going to be equals to pi over 2. Our R is going to, our R is going to be equals to this. And then we're going to have a 90-degree angle. If we continue getting segments along the infinity line, the infinity wire or the infinity line, let me call it. So we're going to have at the point, we're going to reach a point where our R is going to be equals to pi over 2, which is what we have here.
Shawans,
Yeah, sure.
on the same point, since we have Z here in the vertical plane, we also have R there in the horizontal plane, and they are orthogonal, right? That 90.
Yeah, we have here we have R, the grand R, we have the big R, here we have the small R.
The big R. The big R is at 90, right?
Yes, with the wire.
Does it mean that no matter how we can extend this R, it can never be equal to 90, but it can be almost equal to 90 as theta will keep on increasing due to the increment of R, the small r?
You're saying this R, the big R, can be equals to what?
If I got you clearly, you are saying this theta will be equal to 90 as we'll be increasing r, this small r.
Yeah, or as we're so we can decrease it, and we're going to reach this point here. So we're going to have, yes, we're going to have an angle of 90 degrees here.
Or when decreasing it?
Yes, increasing it or decreasing it. So we'll have an infinity line. We've noticed that our theta keeps on increasing as we go. So meaning as we continue to go, there's going to be a point where our theta is going to be equals to 90. Or as we decrease it, also in the negative direction, it's going to be the same. It's going to reach a point where this is a negative infinity. So negative, we've divided the line in two. So we have the positive part and the negative part. So the same thing, as we increase our R. So we've noticed that as we increase the R or the distance dz or the distance z, our R keeps on increasing. So we can conclude that when we reach a certain, it's an infinity line, we do not know its end. So we can assume that when we're going to reach a point where our theta is going to be parallel with our dz, like our R is going to be parallel with our dz, meaning it's going to be at 90 degrees. I don't know if I've answered your question or not.
It's okay. Yeah, it's fine.
Okay. So, yeah, so we can use Gauss law, Gauss theorem or Gauss law, simpler than this. So they can tell you use two methods, or sometimes they'll specify no, use Gauss law. So for Gauss, the Gauss method is actually very easy. It's not, it doesn't involve a lot of steps. So for the using theorem de Gauss, yeah, so it's just one page using theorem de Gauss. So let me just explain this. So using theorem de Gauss, the same thing. So we assume that the line, which is our line here, is passing through a cylinder. So you can remember I said theorem de Gauss cannot be used in closed surfaces. So that's why in this case now we introduce the thing of a cylinder, because we cannot choose Gauss theorem on an open surface. So we introduce this cylinder here. So I have this guy. I have a line. So I have a line. Okay, and then it's passing through a cylinder, this cylinder. So I'm going to draw a fast cylinder. So I have this cylinder like this. Sorry. So I have a cylinder like this. Yeah, so I've got this line is passing through a cylinder. And then I know from the origin, the point, okay, I choose a point from the wire to the surface of the cylinder. That's my R. That's what I read. So meaning if the particle P, the point P is on the surface of the cylinder. So we've got the P point is here, just as I've indicated here. So it's on the surface of the cylinder. So meaning my point P is here, right here. And then this is my grand R, as we stated. So this is my height or my length of the wire. So I know that my champ at this point, my electric field is always in the outward direction. And then I also say that the surface, the direction of the surface area from a surface is also outwardly. It goes in the outward direction. So meaning my champ and my E are going in the same direction. So surface, the vector ds is going to be in this direction, because it's also moving outward. So I'm going to have my point ds here, my vector representing the ds, the surface area is outward. My E is also moving in the same direction. But when I reach at the base of the cylinder, if I move at the base, so if I get a point P on the surface of the cylinder, so imagine the surface of the cylinder, I got a point E. So my E will still be moving in this direction, but my S, my ds is always outside of the surface. It's always moving outwardly. So I'm going to have it moving outwardly. Do you guys get that? Or we can do this the other time we meet. You guys are tired.
I think
The other time.
Okay.
yeah.
All right. So we're going to continue next week, inshallah. Thank you for attending and have a good day.